Okay, today our topic is related to, we can say, we are moving towards the next section of this physical quantities chapter that is
Mhm.
related to precision and accuracy.
Yeah.
Basically, both things are, we can say, related to get the accurate values over there. But if I go towards the precision first, then I will say precision means that how close the values are to one another. How close the values are to one another, then it means it is called precision. And if I go towards the accuracy over there, then I say it tells how close the values are to the true value. Accuracy tells us how close the values are to the accurate value, to the true value over there.
Mm.
If I give little bit examples about here, then if I say, for example, when we are taking a measurement over there and I'm getting some example, like I'm getting 12.1, then I'm getting 12.4, then I'm getting 11.9. So all of these values are very precise. They are very near to each other. When you are measuring some length over there, they are very precise over there. When I
Yeah.
say you are getting, for example, you are getting 12.1, then you are getting 25, then you are getting -3. These values are not precise over there at all.
Yeah.
And if I say towards go towards accuracy over there, then I say, for example, the exact value is 9.8 is the true value for the going towards accuracy. That is true value over there. And I want to calculate this value over there in the form of gravitational acceleration. And when I am going to get the experimental value of my gravitational acceleration G calculation value over there, then I am saying I am getting their value is roundabout, like I am saying 9.7, 9.5, 10, 9.9. It is accurate values are there. If I am getting totally opposite, like I'm getting 5.6, these are accurate values. These are very near to the true value over there.
Mm.
And where, for example, I'm getting 5.6, then I'm getting 12.1, then I'm getting like 7.2. These are not accurate values.
Mm.
So basically, if we compare towards the values of arrangement, that they are how much near to the true value, accuracy will be given. If they are having the precise values, that is not involving any accurate value known over there. For example, if I say these are my precise values, but they are not accurate towards G, if they are even though these are precise, if some amount is precise, it is not necessary that it is true value or accurate value. Sometimes if it is, for example, my precise value are also the accurate values, both cases can be taken down into their values. For example, I am taking also another example over there where I am saying for accuracy, for example, I'm saying this is the circle and this is the main value to be existing. Three values which I am taking over here are going to be taken that they are accurate, they are precise also.
Mm.
If I take in this form that this is the true value and my values are existing all three in this corner. These are values are precise but not accurate. These are
Mm.
precise but not accurate.
Yeah.
Accurate over there. These are precise also, precise plus accurate. And if we go more, for example, I say now, I am getting accurate but not precise. How? Then I will take another circle over here, like I'm taking value 1, value 2, value 3. These are near to my accurate value, but these are not
Not
precise values
precise.
over there. Precise precision is not gone towards them. If I'm getting another value where I'm showing neither precise nor accurate, neither precise nor accurate, over there should be taken in that case. Here I can say they are near to my accuracy value. They are accurate, means they are near to my central man true value, but not precise.
Hmm.
After that, the same case, if I take in case of graph over there to explain the precision and accuracy point of view, let's suppose I take some number of values to be taken in the form of some graphical values, like I am saying here. This is a graph over there. Let's suppose I say this is a graph of true value. True value is taken at this point, and values to be taken to be increased. This is true value, and I am getting my number of values to be taken in this case, number of values like 1, 2, 3, 4, 5, 6. And here I am saying the value over there, like 12.8, 12.9, 12.6, like that is along x-axis. And I'm drawing my graph over there. In this case, I say that true value is having its graph just in the form of perpendicular line over there. And along which I'm saying I'm making a graph over there in the form of a curve wave, like in this form and like in this form over there. In this case, I will say I have both. I have the accuracy, I have the precision over there. But if I am going to take the same graph again to be drawn over here, like this one, true value point is here, and it is having its exact true value will be not changing, like if I say x is equal to 5, like that, its graph line will be shown as a perpendicular line in the positive section over there. But
Yeah.
I am saying here that my waveform is not coming exactly above it. My waveform is coming like this. My waveform is coming like this form. What is happening here? No accuracy,
But precise.
but precise. No accuracy, but precise. If I am taking that my true value and accurate value is going to be taken over there, then I can say, for example, now I'm getting that it should be accurate, but it should not precise in that case. So I'm making a third graph here over there. This is the third graph where I am saying my true value is still there. True value is still there, but my graph is like this form. Now, what I am saying that it is accurate but not precise. Accurate
Yeah.
but not precise. In the last one, where I mostly say over here, like it should not accurate, it should not precise towards its near values over there. Then I will say here, it should not accurate, not neither accurate nor precise. Then this value is going on this form. For example, my true value is here. And what is happening with the precision value is and accurate values over there. This is going to show the waveform and only touching very small value over there just for one time or two times over there. It can
Hmm.
it can be said as neither accurate nor neither accurate nor precise over there.
So usually the accurate ones pass to the center.
Yes, as much accuracy is going to be going on, your precision and accuracy both are going to happen. Then in the graph line, you will have to move exactly in the center. In the first graph, as I have done over here, this is accurate also, this is precise also. In this case, you are saying precision is there, but accuracy is far away. In this case, You are saying precision is there. Uh, Precision is there, but sorry, it is accurate, but precision is not there over
Not
there,
there.
because it is uh, having the values just like in the form of, as we have done, like values are accurate near to this point, but not precision, that are not locating at a single point over there, like to be taken as
Yes.
the average value over there. Their precision is not working for that case.
Hmm.
Okay, after that we will have to move towards errors. Errors, basically we can say there are three main types of errors which are going to happen during any calculation over there. Like difference between true value and obtained value is called error in calculation. The difference between true value and obtained value
Hmm.
is called error in point of view of physics over there. There are three
Hmm.
main types of errors. One is personal
Systematic.
error, like
Okay.
the person who is performing the experiment does not know how to use the operators, how to take the values exactly. He is going
Hmm.
towards the parallax error, or we can say due to lack of knowledge, he is not able to understand what the errors are going to happen over there. At number
Systematic.
three, number two is systematic error.
Then zero.
Systematic zero error is systematic error basically.
Oh, okay.
Systematic error due to faulty operators. Like have taken a vernier caliper which is showing continuously not exactly joining their jaws at zero of
Hmm.
vernier scale and zero of linear scale. It means that is due to faulty operators.
Hmm.
Faulty operators over there. And the third one is random error. Random error is basically, we can say, is going to happen due to repetition of experiment over there. As you are revising the experiment, you are getting the other value. For example, I say to you, measure the laptop screen over there using a meter rule, and you take your value is 10.1 centimeter. Then you take the another value, you say 10.0 centimeter. For the third one, you are taking 10.2 centimeter. So in every repetition of measurement of that length, you are getting some error over there. This is called random error, and it can be minimized by taking the average over there. And
Yeah.
for removing the systematic, for this one, I told you that you will take average value.
And remove anomalous results. Is that also correct?
Yeah, analysis can be removed over there. You will,
Hmm.
in case of random error, you will not get any anomalous value over there. You will get,
Oh.
you will get approximate accurate values over there. Approximate
Okay.
accurate values. And by
Hmm.
removing that error that is due to repetition of that experiment is happening over there, you can take mean, you can take the average value over there. For removing the, we can say, systematic error, we will have to focus on methodology. Like we can say you are going to take zero correction over there. You can go for the better instruments of uh, good calibration over there. Instruments should be improved over there in that case. And you will have to add or subtract by their zero errors, depending upon if it is positive zero error or negative zero error. Then both can be used for removing this error from the main measurement over there. After
Yeah.
that, after knowing little bit about errors, now we are moving towards uncertainty. Uncertainty, basically, the word uncertainty means that we are not certain, we have some doubt. It is the doubt present in our answer due to variation in values over there. We can say, for example, I say to you, get a resistor. You get a resistor of 100 ohm. But in real, due to calibration, due to formation of the resistor, your resistance is not exactly 100. It can be 90, it can be 110. So for getting and removing that value exactly, we take uncertainties to be added, and subtracted from their precise value. As I said 100 ohm, I will say 100 plus minus 10. It means its ranges from 110 to 90 over there.
90.
Then we can say it is uncertainty to be making sure that it is going good on. Okay, according to uncertainty, I will say it is the doubt which is present in our answer due to variation in values, due to variation in values over there. So uncertainty is not to make sure that the value is exact or not. For example, uncertainty can be represented by two main methods over there, as like probability, as like decimal value, or we can say absolute uncertainty. Absolute uncertainty over there. For example, I say I'm using some measurement which is being taken with the help of vernier caliper or meter rule. Let's suppose that is I'm saying 10.5 is my exact measurement. I'm saying here uncertainty is 0.2. It means now I am taking this 0.2 as 20%. That can be taken in the only form of delta x. The change of that value should be taken, that it should be 10.7, it should be 10.3. So giving that range depending upon not making sure that 5 is the exact value over there. If I go towards percentage uncertainty, then I will say here that percentage uncertainty is related to be taken as percentage, delta x as percentage over there. For example, you are getting delta x percentage will equal to delta x over original value of x multiply by 100 over there. For example, in the above statement, you have used two values, 2.2 and 10.5 over there. Here, 0.2 is your absolute uncertainty divided by our least count should be taken over the least count over there, divided by total measurement 10.5 multiplied by 100. You are getting percentage uncertainty over there.
So the original value goes down.
Yes. Original
Okay.
value will be in the denominator. Your least count, your absolute uncertainty can be in the numerator, and multiply by 100, you will get percentage uncertainty in that case. If I simplify using the calculator over there, I get the value that is around about 1.9%, which I will say here for writing this value now, I will say 10.5 plus minus approximately 2% over there. After that, if we go towards fractional uncertainty, it means that I will take least count divided by total measurement. I will not multiply by 100. That is called fractional uncertainty. Fractional uncertainty. If we are taking this one, then we are saying that we are taking the least count in the numerator over there, and we are getting, for example, I'm saying delta x over x. For example, that was 0.2 of the above example divided by 10.5, and this is called fractional uncertainty over there. Okay,
Hmm.
if you want to calculate that to find the uncertainty in a given data over there, then we can simply use uncertainty form that I can take here. For example, what will be the basic formula for uncertainty? I can say that it will be taken as maximum value, like I said, 110 or 20 over there, minus minimum value like in the form of 90 over 2, and then I will get uncertainty of that range over there. There are basic some rules for calculating the uncertainty. That uncertainty should always be smaller than actual value. Like you are taking 10.5, it should not be like uncertainty is 12. Uncertainty should
Hmm.
be always less than this original value. Rules for uncertainty. For uncertainty, rule number 1 states that value of uncertainty should always smaller than original value.
Hmm.
Like the above example, 0.2 is smaller than 10.5 over there. For the law number 2, I will say here that percentage uncertainty should be represented by in significant figures over there. That we can say here percentage uncertainty should be represented by one significant figure over there. That should not be 1.9. It should be only 2 over there. Round off that value over there. And we can also add over there that as we are taking the uncertainty should be not greater than depending upon these values of uncertainties, and absolute uncertainty should not be taken more than significant figures to be multiplying over there will be taken. Okay, right now I am going towards addition, multiplication, subtraction, and division solution for calculating their values over there. Then we are saying here rules for uncertainty. For uncertainty calculation.
Hmm.
The first rule is going for addition and subtraction. Addition and subtraction. For example, I say to you to measure a length using an instrument in the form of some in the form of some length, in the form of some current, in using ammeter, using voltmeter over there. Then you can say here, for example, you are taking two quantities. Quantity A is, for example, I'm saying 25 plus minus its least count, which is the minimum value which it can measure. I can say it is 0.2. For the B over there, I am saying that you have measured the value that is 3.5 over there, plus minus I am saying now it is having the least count of 0.1 over there. Whenever
Yeah.
you are going to add both of them or you are going to subtract both of them, your uncertainties are going to be added. Your least counts should be added always. Means it will be plus minus 0.3. It will also be plus minus 0.3. And you are getting,
Okay.
for example, the value is 25 plus 3,
28.
28.5. If I am subtracting this, 25
Yeah.
में 22, 21.5. But in both cases, your least counts should always be added over there. You are getting plus minus 0.3 in both cases when you are adding or subtracting a quantity over there. Number two rule
Okay.
is then when you are going to multiply with a variable for any quantity over there, then the constant or variable will staying as it is, only that will be taking into account for multiplication coefficient multiplied with a variable like that. For example, when coefficient is multiplied with some variable like that, as you know, the area of circle is taken as pi r square. Then pi is a coefficient which is multiplied with variable r over there. You are taking circumference of circle. 2 pi is a coefficient which is multiplied with your variable r over
Radius.
there. So whenever you are
Hmm.
going to take your such values, which are being multiplied by a coefficient in case of some variable over there, then we can say we will take, for example, I'm saying here that I'm taking example y is equal to 3x plus 2, then 3 is coefficient and x is variable over there. And this is also a constant over there, should not be involved just by taking over formula over there. Then we can say our least count is going to be taken, and it should also be getting the percentage value in separate, and that should be taken and added in the form of value over there. For example, I'm getting here, I'm saying find the area of circle. Do you have calculator with you?
Yes.
Okay, area of circle with the radius 3 centimeter. Okay, first of all, we are
Yes.
using simply the formula area is equal to a radius 3 centimeter plus minus 0.2 कर लेता हूँ यहाँ पे, plus
Okay.
minus 0.2 over there. So area is pi r square, which is equal to pi into 3 square. Kindly get the value. What is the answer?
9 pi, which is 28.27.
28.27. Okay. Now, I will have to move towards the fractional uncertainty to be taken over there in the form of percentage. Then I will say here percentage uncertainty for R. R will be taken as 0.2 over 3. Get it by how much?
0.666 recurring.
Multiply by 100.
Multiply by 100 also? Okay.
Yeah.
6.7 basically.
6.7 means I can say 7% over there. But if I am saying here that uncertainty should be taken in the form of percentage in the separate form, now when you are going to take your area exactly over there, then what will you write? 28.27 plus minus 7%. Now get the 7% of 28.27.
Okay. That's 2 basically, 1.97.
28.27 plus minus 2 is the total area in centimeter square over there. This was
Yeah.
the rule number 2 over there.
Yeah.
After that, multiplication and division of the variables should be taken into account. In case of multiplication and division of two measurements, for example, multiplication and division.
This was only multiplication or
This is
percentage?
coefficient multiplication.
Okay, okay.
Multiplication and division. For example, I am taking here the formula which is related to both the measurements over there. I am saying to you V is equal to IR. Okay. Yeah, for the division, I'm taking R is equal to V over I. I am saying to you, I am giving you M meter and ohm meter. I am not using there. Where to go? Where to go? Where to go? Here. Can you see the screen now?
Yes.
Okay. For example, I'm saying there is a current, there is a resistance which we are taking here. Current is being measured using ammeter. I'm saying
Yeah.
you are measuring the value that is 0. Not 0 point, I'm getting some exact value, like 5.3 ampere with the least count of 0.1 ampere. Current is measured in the form
Yeah.
of I. And for
Hmm.
resistance, you using ohm meter or digital multimeter over there, and you are measuring your resistance as 25 plus minus with least count is taken as 1 ohm. And I'm saying
Hmm.
to you, go for calculation voltage over there. You are going V is equal to IR. Okay. IR, then you are getting 5.3 multiplied 25. How much?
5.3 multiplied 25. 132.5.
After that, now you are going percentage uncertainty for current. It is 0.1 over 5.3 multiplied by 100. How much?
0.1 divided by 5.3 times 100. Uh, 1.88.
88%. Okay. Now moves towards percentage of resistance. That will be taken as 1 divided by 25 multiply 100. That is
4.
4%.
Yes.
Okay. Now add both of these percentages.
6.
So 6%. So that will be added with your voltage value. Like I am saying here, voltage will equal to 132.5 plus minus 6%. 132.5. Get the percentage value of 6.
6%
6%
of
of
1.
132.5.
That's 8. 7.95.
7.95, and you can get 132.5 plus minus 8 volt is the voltage over there. When the division is going on, now you can take the voltmeter reading, you can use the ammeter reading, and you can use those values. Do by yourself by taking the supposed values and then add the percentage, and in the final quantity get that percentage to be taken for that resistance value to get in ohms form.
Yeah.
Is it clear?
Yes.
Okay. Division, multiplication, and last one is related to power. Related to
Okay.
power over there. As I have given to you the example over there, like where we have done for pi r square, like 7% I have taken here. Then I am going to tell you that when there is power 2, then this when there is power 2 on r square formula over there, then this percentage uncertainty will be multiplied by power, and you are getting 14% over there, and multiply by 2, and now get the value of this percentage uncertainty for the area over there. 28.7 multiply 14%. Get the 14% of this value. When the power is there on the
4
variable,
point.
then
Yeah.
uncertainty will be multiplied by that power. How much?
4.
4 is there. Okay. The next law is related to power on the variable. Will be taken into account. Power on the variable. Okay. Power on the variable, we have taken the example in case of area. Now I am taking the case for volume to be measured of a sphere, like power on variable. Then how we will go for uncertainty over there. Then for example, I am taking here the formula of sphere volume is equal to 4 by 3 pi r cube, and I say the r which is measured by using vernier caliper or screw gauge over there, or some other instrument of length measuring over there. I am saying the radius is 5.5 centimeter plus minus 0.02 centimeter, like that. This is the least count for this one. So for first of all, for getting the volume 4 by 3 pi into 5.5 cube, how much you are getting the value over there?
4/3 times 5 times 5.5.
Yeah,
It's 696.9.
696.9. Okay, this is the volume
Yeah.
in centimeter cube over there. For going towards the radius in the form of percentage uncertainty, I will say here 0.02 divided by 5.5 multiply 100.
It's 0.36.
0.36 after multiplying by 100.
Yes, after multiplying by 100.
Okay, this is the percentage, that 0.36% value over there. Now we should move towards to be multiply it by 3, because the power of the variable r is 3 over there. Then I say that percentage uncertainty should be multiplied by 3, 0.36. How much? 1.08 or 18?
1.08.
0.08%. Then for getting the volume over there, I will say 6.96.9 plus minus 1.1% over there. So 1% is 696 multiply 1 divided by 100 will be 0.696. Check the answer of 1% of this value.
1% of 6.96 is 0.0696.
Okay, 696 0 696 6
696 या 6.96.
बाबा 696 है
ओ ओके ओके ओके, मैं फिर से करता हूँ. 1% of 696 चाहिए.
जी
6.96.
696
The answer is 6.96. 1% of it.
696.9.9 is plus minus 6.96. So this is the whole way how to go with it. For
Yeah.
uncertainties calculation and for precision and accuracy, this is the topic which is related to precision and accuracy of physical quantities. This was the second section of our chapter. Tomorrow we will also tomorrow no, we will go for Saturday, I think so.
Yes. Yeah.
Yeah.
Chemistry.
Yeah, Saturday, Sunday chemistry, and Monday, Tuesday is for physics. But don't prolong the class for next time, okay?
Yeah. 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 Sure. Sure. Inshallah.
Okay, thank you so much for today.
Okay. Thank you, teacher.
Allah Hafiz, Allah Hafiz.
Allah Hafiz.